Hello, everyone. Good afternoon. Happy Wednesday to you. Nice to see you all. I hope you're doing well. Hope the week is going well so far. Let's see. Before we get started here, we're talking about thermal chemistry, as you know, and I see this is my thing here is wrong. This should be chapter 7, not chapter 9. So I'm not sure what happened there, but let me just change that. All right, save. So thermochemistry, remember, is the relationship between energy and chemistry, right? So we started looking at some definitions of different important quantities like energy and work. We looked at the first law, right, which tells us that the total energy is constant, right? So we don't have energy being created nor destroyed, but energy is transferred between the system and the surroundings, okay? And so that we're gonna kind of think of all these energy transfers from that point of view. Then we talked about one way that energy can be transferred, and that's through heat, right? So if two objects are a different temperature, the hotter object will transfer energy to the colder object via heat, right? And we can track that with this equation, Q is equal to MC delta T, okay? And we learned about heat capacity and how to calculate this Q, this energy that's transferred due to heat, all right? And then last time, let's see, where were we? That's wrong. Right here. We looked at quantifying work, right? And I think we ended right here where we said, okay, work was equal to minus P delta V. So the kind of work I'm talking about is the kind of work that occurs like in a cylinder, like this, like in a car, all right? And when this cylinder expands, it does work on the surroundings, right? So in a car, when this happens, this drives the car in the forward direction, right? It does work on those surroundings. The total amount of work done is given by this equation. W is equal to minus P delta V. W is the work, okay? Since work is a kind of energy, right? It has the units of joules, just like heat does, all right? P is the pressure. Pressure, and it's the external pressure. So in other words, it's the pressure that this is pushing against as it expands, all right? And delta V is the change in volume. V2 minus V1, all right? So you can see in terms of the sign of this, right? If V2 is greater than V1, then work is negative. So for an expansion, like you see here, from going to here to there, right? You're doing work on the surroundings, the system loses energy, right? And the surroundings gain some energy, right? So work is negative. Remember, when energy leaves the system, what sign does that carry?
Negative.
Negative sign, right? That carries a negative sign. When energy leaves the system, that carries a negative sign. On the other hand, if V2 is smaller than V1, so if you go this way, right, and V2 is smaller than V1, then delta V is negative, so work would be delta V is negative, work would be
Positive.
positive, right? Work would be positive. And so if this piston is going down, right, then work is being done on the system, and that's positive, okay? So expansion, energy goes out of the system to the surroundings. Compression, energy comes into the system, okay? Important there to understand those signs. All right, let's do an example just so we can understand the units here. If you do, let me give you the units here are going to be atmospheres liters, right? And of course, energy is joules, but those units are, you can convert between them. So in order to use this equation, we also have to use the relationship 1 atmosphere liter is equal to 101.3 joules. All right. So atmosphere liters, if you work that out, the units that are contained in that, you get what that's equivalent to 101.3 joules. All right. So you can just use that as a conversion factor. Okay, let's do this problem. So we're given that a cylinder expands a constant pressure. So the constant pressure is 1.05 atmospheres, right? And it has an initial volume of 225 milliliters, right? And it expands to a final volume of 772 milliliters. And you want to find W, the work. Okay? So we're going to use this equation. Work is equal to minus P delta V, right? So that's equal to minus the pressure, 1.05 atmospheres, times delta V. Delta anything is always final minus initial, okay? So that's V2, 772 milliliters, minus 225 milliliters, all right? So now the only thing is that this is in milliliters, and our conversion factor is atmosphere liters, so we have to convert that to liters at some point, okay? But this difference turns out to be equal to minus 1.05 atmospheres times 547 milliliters, right, is equal to minus 1.05 atmospheres times 0.547 liters, all right, which is equal to negative 0.574 liter atmospheres. All right, and then now we just have to convert from liter atmospheres to joules, all right, times 101.3 joules per liter atmosphere, right? And then this cancels with that, and we get negative 58.2 joules. Does that make sense? All right. Let's have you try one. Go ahead and try this one and enter your answer in the poll. So just a little hint here, right? I gave you the total volume of the expansion rather than giving you V1 and V2 like in the one I did, right? So if you have the total volume of the expansion, if it's an expansion, then what's bigger, V2 or V1? In other words, what's the sign of delta V in this case?
Positive.
Positive.
Yeah.
Delta V is positive. So keep that in mind when you plug that into this equation. Delta V is positive because it's an expansion. V2 is bigger than V1. I'm telling you that because I know some of you are getting the sign wrong. Think of what the sign should be here. Should it be negative or positive? Don't answer that. Just think about it as when you're answering your question in the poll. Okay, about 10 more seconds. Okay, the right answer was B. The only other significant answer really that was put down was A, and that's just the wrong sign, okay? You gotta remember that the equation, right, is W is equal to minus P delta V, right? That's the negative sign. So when you do that, you go negative 1.50 atmospheres times 2.55 liters. That gives you 3.83 liter atmospheres. And then you multiply that by 101.3 joules per liter atmosphere. And that gives you negative 387 joules for the answer. All right. Does that make sense? Any questions? Okay, so we now see that a system and its surroundings can exchange energy via heat, right? Or via work, or via both, right? They can both happen simultaneously. Delta E, then the change in energy is always going to be Q plus W, the sum of heat and work, okay? Because you have to take both of those into account. Now, one way we can measure the amount of energy being given off by a chemical reaction is through something called constant volume calorimetry, all right? And constant volume calorimetry measures delta E, the change in internal energy. Remember, last time we defined E as internal energy, right? Remember, internal energy is the sum of all the potential and kinetic energy of the system, okay? So the change in internal energy is equal to the amount of heat exchanged and the amount of work done summed together, all right? A way to measure delta E for chemical reactions is through a technique called constant volume calorimetry, all right? And constant volume calorimetry uses what's called a bomb calorimeter. And what you have is you have basically a big bucket that is thermally isolated from the surroundings, okay? So it's insulated. And inside of that, you have what's called the bomb, which is a compartment that is airtight, all right? And cannot change volume. And then you have a sample that is undergoing some reaction, right? And usually, like for example, combustion, you would ignite it and then see it burn in oxygen, okay? And because of the change in energy with the surrounding, so that your reaction is the system, right? It's exchanging energy with the surroundings, and it can exchange energy via heat or work, right? And so if you sum those two together, you'd get delta E. So the key to this, though, is that because this compartment cannot change volume, delta V equals 0, right? So if delta V equals 0, that means no work, right? No work is done. And if no work is done, then delta E is just equal to Q. And we put a little V there to say constant volume. Right? Because if you have delta E is equal to Q plus W, and you make W equal to 0, right, then delta E is just equal to Q. Does that make sense? So that's what's going on here in this bomb calorimeter. And so all you got to do then is say, okay, if you want to find delta E for this reaction, then all you have to do, instead of measuring Q and W, you just have to measure Q, because W is 0, right? So how do you measure Q? Q is the amount of heat being given off. That heat goes into the calorimeter and raises the temperature of the calorimeter, and you can measure that with a thermometer, right? So you can get delta T. And then we write that Q calorimeter, the amount of heat, let me do it this way. Q reaction is equal to minus Q calorimeter, right? Because you have your reaction, right? And the surroundings are the calorimeter, right? And energy is only being exchanged via Q. There's no work, right? So it's just heat. So whatever heat is being given off by the reaction is absorbed by the calorimeter, right? So Q is equal in magnitude for both of these, but opposite in sign. Okay? So then Q calorimeter is just equal to the heat capacity of the calorimeter times delta T, all right? This heat capacity is for this whole calorimeter assembly, all right? And usually that has to be measured in a separate experiment, okay? But once you have that, then you can figure out what Q calorimeter is. Once you have Q calorimeter, you can figure out Q reaction. Once you have Q reaction, you can get delta E. All right, so let's do an example. All right, so we're given that you have 1.588 grams of A, and you're given its molar mass. Is burned in a bomb calorimeter. The temperature rises, so then we get T1 is equal to 23.45 degrees Celsius. Then to a higher temperature, T2 is equal to 26.11 degrees Celsius. So which way is energy going in this case? If the temperature is going up, which way is energy going? From the system to the surroundings, or from the surroundings to the system?
System to the surroundings?
Yeah, system to the surroundings, right? The surroundings are getting hotter, right? So energy is going that way, okay? So T1 is equal to 23.45, T2 is equal to 26.11, and then you're given C calorimeter is equal to 4.58 times 10 to the third joules per degree Celsius, and you want to find delta E for the reaction in kilojoules per mole, okay? All right, so so we're going to do this. Solving this is going to require 3 steps. Okay, in the first step, we're going to find the amount of heat absorbed by the calorimeter. How are we going to do that? We're going to say Q cal is equal to C cal times delta T. All right, that's the first step. That's the amount of heat absorbed by the calorimeter. And then we're going to say, okay, the amount of heat absorbed by the calorimeter is equal in magnitude but opposite in sign to the heat being given off by the reaction, right? So Q reaction is equal to minus Q calorimeter, right? So that's the amount of heat being given off by the reaction is whatever Q calorimeter is, but you just take the opposite sign of it, right? And then in the third part, we're going to say delta E is equal to Q reaction divided by the number of moles that reacted, right? We're just going to divide by the number of moles because that way we're going to get joules per mole, which is what it's asking for, right? Find delta E in joules or kilojoules per mole, okay? So let's dive in and do this. So we'll do the first part. So this is part number 1. Q calorimeter is equal to C calorimeter times delta T is equal to 4.58 times 10 to the third joules per degree Celsius, right? Times delta T. Delta T is T2 minus T1, right? So 26.11 minus 23.45. Right? That whole thing is 2.66 degrees Celsius, right? And notice that that's going to be positive, right? Because the calorimeter is getting energy in, right? So the sign of that should be positive, all right? And if we work that out, we find that that's equal to 1.22 times 10 to the 4th joules. Okay? Does that make sense so far? Good. Okay, the next step then is say, okay, well, Q reaction is just going to be, so step 2, Q reaction is equal to minus 1.22 times 10 to the 4th joules, right? Q reaction is equal to minus Q calorimeter, right? Because they're equal in magnitude but opposite in sign, okay? Then step 3, we're just going to take this and divide by the number of moles, right? Divided by number of moles, right? How do we figure out the number of moles? Well, we know the grams, and we know the molar mass. Right, so this is going to cancel, right? And we're going to get moles, and that turns out to be 0.0102 moles. All right, so then we just do minus 1.22 times 10 to the 4th joules divided by 0.0102 moles, and that gives you negative, let's see, negative 1.20 times 10 to the 6 joules per mole, or negative 1.20 times 10 to the 3rd kilojoules per mole if you convert to kilojoules. Oh, wait a minute, is that right? 1.22 times 10 to the, yeah, that's right. Does that make sense? So it's just those 3 parts. Figure out Q calorimeter, figure out Q reaction, then figure out Q reaction per mole. Right? That's how you work these kinds of problems. You ready to try one yourself?
Wait, I have one quick question. How do you get from, for step 3, how do you get from the minus 1.22 times 10 to the 4 joules to, I guess, to 0.0102 moles?
Okay, so this is the number of joules I figured out from here, right? And I want to divide by the number of moles. So I got to figure out how many moles I had. So I went over here and I said, okay, I had this many grams and I know the molar mass, right? So I figured out how many moles I had. And then I took that and I divided it by the number of joules. So that's going to give me joules per mole.
Okay, so you divide that, and that gave you 1.588. No, that was, never mind, that was the grams.
That gives me this.
Okay. Okay, I'm gonna
That
take a
makes sense?
screenshot of this for a second. Okay, cool. Thank you.
Yeah.
I also have a question about something.
Sure.
So this might be like a tiny bit off topic, but for the lab tonight, it says change in H reaction equals Q reaction over N. Is that, and it's the enthalpy, is that the same as what we just did?
Sorry, say that one more time. I didn't quite catch it.
Sorry. For the lab tonight, it says change in H reaction equals Q reaction over N.
Yeah, okay.
Is that the same thing as this?
It's not quite the same thing. I'll explain to you the difference here in just a minute.
Okay.
This is how you measure delta E, okay? In a bomb calorimeter, you measure delta E. In a coffee cup calorimeter, you measure delta H. And so we'll talk about that in just a minute. But the concepts are very, very closely related. So it's this very, 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 very similar idea. There's just a small little difference, and I'll explain it to you in a minute, okay? But first, let me have you try this one. Try this problem.
This is just a minor question, but why is the degree symbol underlined?
I don't know.
Okay.
Just with that. I don't know why I did that. Computers have a mind of their own sometimes.
Wait, quick question. What does it, does it say mole where it says on number 3 changing equals Q reaction over, is that mole?
Oh yeah. Right here?
No, it's on the number 3 where it says changing equals. Yeah. Does that one say mole?
Yeah.
Okay.
Can you move your paper up a bit?
Pardon me?
Can you move your paper up a bit?
Oh yeah.
Sorry, thank you.
I have a question.
Yeah.
Yeah, for the heat of the calorimeter, why is the mass not considered in the equation?
Sorry, Javier, I couldn't quite catch the last of that. Something you were asking something about the calorimeter?
Yeah, I was asking why is the mass not considered in the equation? In calculating the
Do you mind typing your question in the chat? Because for some reason your volume is breaking up on me.
okay.
Can't quite hear you for some reason. Oh, yes. Okay. Very good question. So for these types of calorimeters, the calorimeter, the heat capacity is for the entire calorimeter assembly. It includes the metal and the water and everything else. So it has to be calibrated for that specific calorimeter, right? So, yeah, let me get back to that. Let me finish this, and then I'll expand a little bit more on your question. Okay, Javier, hang on for a second. All right, let's see. Try to see if you can finish this up in the next minute or so. I'll give you one more minute to see if you can finish up this calculation. Most of you that have finished it have gotten it correct. So nice job.
I remember from Monday, I noticed when looking through the recording that the lecture was chapter 9, and it was like really confused at first.
Yeah, sorry about that. I don't know what happened there either. It should be chapter 7. All right, a couple more seconds here. If you got an answer, type it in. All right, I'm going to end that here. And the right answer was D. And lo and behold, look at that. Most of you got that. So nice work. If you're still struggling with it, again, you're going to have 3 parts, right? In the first part, you're going to calculate Q calorimeter, which is equal to the heat capacity of the calorimeter times delta T. And the question that Javier had was, well, why isn't there a mass in here? Why isn't it not MC delta T? Because the equation we have is that Q is equal to MC delta T. But remember, this is specific heat capacity in that equation, right? In MC delta T. These together, multiplied together, can just be one heat capacity, right? So for example, if I have, what's the heat capacity of 10 grams of water, right? The heat capacity of 10 grams of water would be C equals 10 grams times 4.18 joules per gram degree Celsius, right? That would give me 41.8 joules per degree Celsius, right? That's the heat capacity of 10 grams of water, right? So this heat capacity here is kind of like that, right? It already takes into account all the masses of all the different things and all the different heat capacities in the calorimeter, right? And so that's why it doesn't have a mass in it, because that's already built into that. Does that make sense? So notice the units, instead of being kilojoules or joules per mole degree Celsius, is just kilojoules per degree Celsius. All right? All right, so you plug into that and you get 5.86 kilojoules per degree Celsius times 39.8 minus 23.5 degrees Celsius, right? And the degrees Celsius are going to cancel, and you're going to get 95.5 kilojoules, right? So then that's step 1. Step 2 is Q reaction is equal to minus Q calorimeter. So that's equal to minus 95.5 kilojoules, right? And then delta E is going to be equal to this divided by the number of moles. Divided by the number of moles. And the number of moles is the given mass, 4.25 grams, times, we're going to use the molar mass, 1 mole over 84.16 grams, and that's going to cancel, and that gives us 0.0505 moles, right? And then we divide that by 0.0505 moles, right? And we get negative 1.89 times 10 to the third kilojoules per mole. Does that make sense?
I have a question.
Yeah, Michael.
I do understand the process of steps. Just initially, I felt like it was hard to identify what was the C calorimeter.
Yes.
How do you like know right away? I mean, I kind of just looked for a cue from the previous example, but.
Yeah, notice it says right here, in a bomb calorimeter with a total heat capacity of 5.86.
Okay.
Right. So you kind of, so it'll either say C equals that, or it'll say heat capacity of the calorimeter equals that.
Okay.
But it should tell you one way or the other, it should indicate that. But in this case, when you see this total heat capacity, you say, oh, okay, that's C for the calorimeter.
Got it.
Okay, good question. Any other questions? Okay, so that, that process gives you delta E, right? Because again, remember what you're doing. Delta E is equal to Q plus W. In a bomb calorimeter, you're making it so that work is 0. So delta E is equal to Q, right? You measure Q, and that's equal to delta E, right? Now, a lot of times in the lab, you're not interested in delta E. Because delta E is a term that tells you both the heat and the work, right? It's equal to both of those, okay? A lot of times you just want to know, oh, and also a lot of times in the lab, you don't carry out reactions in a container with a constant volume, right? When you carry out a reaction in the lab, or when you burn methane on your stove, right? You're not holding the volume constant, right? You're letting it expand into the atmosphere, right? And so there's another quantity that it's more useful if you want to just know, okay, how much heat is this chemical reaction going to give me under normal conditions, right? Not under these sort of forced conditions of a bomb calorimeter, but under normal conditions. When I carry out the reaction on the lab bench, or when methane burns on my stove, right? How much heat is given off, all right? That quantity is called delta H. So that's the heat emitted, not at constant volume, but at constant pressure. And you don't have to overthink this, right? All you have to do is think about delta H is the amount of heat released under ordinary circumstances, more typical circumstances. Right? Not under sort of a constrained thing. So there's a little bit of a difference between delta E and delta H. Delta E we measure in a bomb calorimeter. Delta H we measure in what's often called a coffee cup calorimeter. This one's under constant volume. This one's under constant pressure, okay? This is the value that is more useful in terms of how much heat is given off by a chemical reaction under sort of normal conditions. This is more important kind of from a theoretical point of view, okay? Let's see. Just to summarize all that really quick. Delta E is equal to Q plus W, right? That's always true. But in a bomb calorimeter, right, W is equal to 0. Okay, so in a bomb calorimeter, delta E is equal to Q under constant volume, right? That little V just means constant volume. All right, so that's a bomb calorimeter, right? On the other hand, in the lab, you don't have constant volume, you have constant pressure. And by a lab, I just mean under ordinary circumstances. It could be your kitchen stovetop or whatever, right? In that case, delta E is equal to QP plus W, right? And so the amount of heat, QP, is equal to delta E minus W, and that's equal to delta H, okay, which is the change in enthalpy. So again, don't overthink this too much, all right? Delta E and delta H are kind of similar in many ways and actually many times have very similar values, okay? There's just a subtle difference between them. Delta E is more theoretical. You measure delta E in a bomb calorimeter. Delta H is more practical. You measure delta H in a simpler coffee cup calorimeter, okay? And that's called the change in enthalpy. And for the rest of this chapter, we're going to focus on delta H because, again, that's the more practical quantity. All right? For an exothermic reaction, delta H is negative, right? A reaction that gives off heat, delta H is negative. Energy is leaving the system. Just like money's leaving your bank account carries a negative sign. An endothermic reaction, delta H is positive. Energy's coming into the system, right? Just like money coming into your checking account, okay? So for example, chemical cold pack, right? Like the kind that we've talked about previously to ice athletic injuries, energy comes into the system, right? That's endothermic. So that would be positive delta H. Burning a natural gas flame, energy comes out of the system. That would be exothermic. Okay, that would have a negative delta H. So positive delta H, negative delta H. Delta H has its own stoichiometry, just like other kinds of stoichiometry that we've looked at. So for example, let's say we have this problem. How much heat is evolved in the complete combustion of 13.2 kilograms of C3H8? So here's the reaction written out, and here's delta H for that reaction. Delta H is equal to minus 2044 kilojoules. Notice this doesn't have kilojoules per mole because it depends on moles of what that you're talking about, right? So the stoichiometry here of delta H is just like all other stoichiometry that we've learned. So we can say from this equation, right, from this what's now a thermochemical equation, right, because it also gives the delta H, that 1 mole of C3H8 negative 2044 kilojoules, right? But what if you want to know it with regard to oxygen? Well, then you have 5 moles of oxygen proportional to negative 2044 kilojoules, right? Or let's say you want to know how much heat is evolved per amount of CO2, right? Well, it'd be 3 moles of CO2 for every negative 2044 kilojoules, right? So this becomes a stoichiometric relationship, just like 1 mole of C3H8 is proportional to 5 moles of oxygen, right? We've used these stoichiometric relationships all the time. This is just a new set of stoichiometric relationships that involve reactants and energy, okay? So if we want to know how much heat is evolved in the complete combustion of 13.2 kilograms of C3H8, we got to convert that to moles and then use this to convert to kilojoules, right? So we would write 13.2 kilograms times 10 to the 3rd grams per kilogram times, and then we convert it to moles, 1 mole over 44.09 grams. That's the molar mass of C3H8, okay? And then times negative 2044 joules per mole. And you get a bunch of canceled units here, right? Kilograms, kilograms, grams, grams, moles, moles, right? And you get joules. You get minus 6.12 times 10 to the 15 kilojoules. Does that make sense? Right? I went grams to moles, but now instead of going to moles of another reactant, I went to joules, right? Using the stoichiometry from the reaction. What would be different here if I was going to, if I wanted to know, the amount of energy for a given amount of oxygen? Well, first I'd convert to moles of oxygen, but what would I use here?
You would have
Over 5 moles.
yeah.
Correct, exactly right. You'd have this number over 5 moles. Okay, let's have you try one. Go ahead and try this one.
Wait, Charles, I got a quick question.
Sure.
What exactly is that like negative 2044? Is that like, let's say in the context of that equation, was it the flame? And then
So this is the amount of energy that it's emitted when 1 mole of C3H8 reacts with 5 moles of O2 in that
Okay.
reaction. Right? It's the total amount of energy emitted.
for the whole reaction, right?
Correct.
And then what exactly is that number that we found?
The number that you found was the amount of energy that is released when 13.2 kilograms of this reacts.
Oh, okay.
Okay?
I got it.
Right? So this is the amount when 1 mole reacts. What we found was the amount when 13.2 kilograms reacts.
Gotcha.
So this is very similar. This is saying if you burn 1.32 times 10 to the 5th kilograms of hydrogen, how much heat is evolved? This is the amount that is evolved when 2 moles of hydrogen reacts with 1 mole of oxygen.
I see. I understand now. Thank you.
You're welcome.
The final answer that you got for the very last one, is that raised to 15?
Yeah.
Okay.
Is that right? Wait a minute.
Because I got it raised to the 5, I think.
Yeah, should be a 5. Sorry about that. Thank you for catching that. That should be to the 5, not the 15. Remember this 2 right here, right? Don't forget that that 2 has got to be part of your calculation, right? The conversion factor here is 2 moles H2 is proportional to negative 571.6 kilojoules. Okay, about 10 more seconds. Try to finish it up in 10 seconds. Okay, so the right answer was B, and most of you got that, but a few of you put A, and the reason you put A is you forgot that 2, right? So the way you do this is you start out with the mass of H2, and I just converted that to grams, so it's 1.32 times 10 to the 8th grams of H2 times 1 mole over 2.02 grams, right? That tells you the moles. And then times, and here's the important part, minus 571.6 kilojoules for every 2 moles of H2, right? And why the 2? Because notice there's this much energy being given off for every 2 moles of this, okay? So this all cancels, right? And you get kilojoules, and you get that that's equal to negative 1.87 times 10 to the 10 kilojoules.
I have a question.
Yep.
Okay, so when you wrote down the 1.32 times 10 to the 8th or to the 5th power?
1.32 times 10 to the, oh, I see. Just convert grams to grams. So I can, that's,
oh, okay, got it.
yeah, I just converted that in my head to grams. Any other questions that make sense? Everybody good? Okay, very good. Let's move on. So the next thing I want to talk about then is this constant pressure calorimetry, and that's how we measure delta H. Okay, so remember, bomb calorimetry measures delta
E.
Delta E, all right? Coffee cup calorimeter or constant pressure calorimeter measures delta H, okay? So here's a typical coffee cup calorimeter. It's much simpler than the other one. You just have a couple of styrofoam cups that will insulate and not allow heat to transfer back and forth, right? You have a stirrer and a thermometer, and then your reaction's going on inside of this calorimeter in water, okay? The difference is, one of the important differences here is that for a bomb calorimeter, you have your reaction, and then you have the calorimeter as the surroundings, right? So you have Q reaction equals Q calorimeter. In a coffee cup calorimeter, the rest of the calorimeter, there really isn't much to it, right? So when you have your reaction, all that heat only gets transferred to the water, okay? It just goes into the water instead of to the whole calorimeter assembly because it's so much simpler, right? This styrofoam really is just an insulator. It doesn't have much heat capacity, right? So you can just assume that all the energy is just going into the water, okay? So let's do an example of a coffee cup calorimeter problem. You're going to want to use Q for the water, or in some cases, the water could be a solution as well. right? But usually it's an aqueous solution. But usually we assume that the heat capacity of that is 4.18 joules per gram degree Celsius, right? Which is just the heat capacity of water, okay? So, so you have your, let's just do this example. Okay, so you have this reaction, right? And you're given that you have 0.158 grams of magnesium is combined with enough HCl to make 100 milliliters of solution. All right, so this is the solution, but it's mostly water, right? So we're going to assume the heat capacity is just the heat capacity of water, okay? And then T1 is equal to 25.6 degrees Celsius. T2 is equal to 32.8 degrees Celsius, right? And the density of the solution is given as 1.00 grams per milliliter, and the heat capacity is given as 4.18 joules per gram degree Celsius, right? And we want to find delta H. All right, so the procedure here is going to be very, very similar to the one we just did for the bomb calorimeter, okay? It's going to be 3 steps. 1, you're going to find Q of the solution now. Why the solution? Because all the energy is going into the solution, right? Before we found Q of the calorimeter, now we're just going to find Q solution. All right, and what is Q solution going to be equal to? It's going to be equal to the mass of the solution times the heat capacity of the solution times delta T. That's the first step. Second step, Q reaction is equal to minus Q solution, right? Just like before, the only difference is we're replacing the solution with the calorimeter. I mean, the calorimeter with the solution, right? And in this case, we're using the mass of the solution times the specific heat capacity of the solution to get the overall heat capacity of the solution. All right, so Q reaction, and then lastly, delta H is equal to Q reaction divided by the number of moles that reacted, right? So it's very, very similar process, okay? So let's just carry out each step here. The first step, right, Q solution is equal to 1.00 times 10 to the 2 grams. Why is that? Because I have 100 milliliters and the density is 1 gram per milliliter. So therefore I have 100 grams. So I have 100 grams of solution times 4.18 joules per gram degree Celsius times delta T, right? Which is T final minus T initial, 32.8 degrees Celsius minus 25.6 degrees Celsius, right? Notice that my grams and my grams are going to cancel. Degrees Celsius and degrees Celsius are going to cancel, right? I'm going to be left with joules. That part comes out to be equal to 3.0 times 10 to the 3rd joules. Okay, that's the first step. Second step, Q reaction is equal to minus 3.0 times 10 to the 3rd joules, right? Because Q reaction is just equal to minus Q solution. And that makes sense, right? Because the reaction is giving off heat. The solution is the surroundings of solutions is warming up, right? So the solution is gaining heat. The system or the reaction is losing that heat, okay? And then lastly, the third step, delta H is equal to negative 3.0 times 10 to the 3rd joules, right? Divided by the number of moles. You can figure out the number of moles because we're given the mass, right? The molar mass. So the number of moles is equal to 0.158 grams times 1 mole over 24.31 grams. That cancels, and I get 6.50 times 10 to the minus 3 moles. All right, so that's going to go there. 6.50 times 10 to the minus 3 moles, right? And so delta H is going to be equal to minus 4.6 times 10 to the 5th joules per mole. And that's per mole of magnesium, right? So if I were to write that reaction for 1 mole of magnesium, I would write magnesium plus 2HCl goes to MgCl2 plus H2. Delta H is equal to negative 4.6 times 10 to the 5 joules.
I have a question about this.
Yeah.
Why do you only use the grams of magnesium when you're doing the moles?
Great question. Because notice that the reaction is the reaction of magnesium and HCl, right? The water is just the medium in which it's happening.
Oh, okay.
Okay? The water is not reacting. So I want to know because this is the reaction, I want to know, okay, and there's a 1 here, right? I want to know how many moles of magnesium do I have? Because that is going to be the number of joules that are given off per 1 mole of magnesium. Does that make sense? Good question.
Would you get the same thing if you're doing it for HCl?
So if you figured this out for HCl, you would get a number that was per mole of HCl.
Mm-hmm.
But then if you were to write the equation like this, what would you have to do to that number in order to make it match the equation? You'd have to multiply by 2,
Oh, okay.
right? Because there's a 2 here. So this will give you the amount, when you divide by the number of moles of the reactant, it'll give you the amount per mole of that reactant. If the coefficient is 1, then that's the same thing for the entire reaction. If the coefficient is something other than 1, then you have to multiply by that coefficient.
Okay, so if magnesium had 2, then that it would change.
This would have to be twice that.
Okay.
Okay.
Can you move your paper down a bit? Yeah, just so I can see that, like the beginning of your work. I think, yeah.
Okay, I had a question for you, but I notice I'm running out of time. I'm going to put it in here just in case you want to go back and work this problem out if you want to rewatch the recording, and also for those of you that are watching the recording. I'm just going to put this question up here. If you're going to work this out, just pause the recording right here, work it out, and then the correct answer is B. Okay, the correct answer is B. So I'm not going to take time in class right now to do that because we're running a little tight on time and I have another topic I need to get to, but you can always go work this out after class, okay? It's very, very similar to the one we just did. All right. The last topic I want to talk about briefly is the relationships involving changes in enthalpy. All right. So if you have some reaction like C plus O2 goes to CO2, and you know delta H for that reaction, all right? If you have a reaction like that and you multiply it by some factor, then delta H is multiplied by that same factor. So for example, if I multiply this whole thing by 2, right? So if I write 2 carbon plus 2 O2 goes to 2 CO2, right? Then delta H would equal 2 times negative 393.5 kilojoules, which would equal negative 787.0 kilojoules. Okay, so if you have a reaction and you multiply by a factor, you multiply delta H by that same factor. if you have a reaction and you know delta H for that reaction and you reverse the reaction, so here's number one. If you reverse the reaction, so for example, if I have CO2 now goes to C plus O2 instead, right? Then delta H for that reaction is just equal to delta H for the forward reaction with the sign changed, right? So delta H for this reaction would be plus 393.5 kilojoules. Okay? So if you multiply a reaction by a factor, you multiply delta H by the same factor. If you change the direction of the rubber reaction, you change the sign of delta H. All right? And then lastly, if you can express a reaction as a series of steps, then delta H for the overall reaction is the sum of the delta H's for each step. So for example, if I have A plus 2B goes to C, right? And I know delta H for that. And then if I have C goes to 2D, and I have delta H for that, I can sum these two together, right? And I get the reaction A plus 2B goes to 2D, and delta H for that reaction is just the sum of delta H1 plus delta H2. All right? So those are three fundamental sort of relationships involving delta H, okay? And we can use those to calculate delta H for an overall reaction. So for example, if you just look at this in pictures, right? The reason this works is because here's A plus 2B, here's delta H1 going to C, here's delta H2 going to D, right? And so delta H from here to here is just the sum of those two. All right? All right, what kind of problems will we have to do involving these laws? It'll be a problem kind of like this one, all right? Where you're given some reactions and some delta H's for those reactions, and you're trying to find delta H for a related reaction, okay? This kind of problem sometimes requires just a little bit of playing around with, right? So what you're trying to do is get these three reactions to add up to this reaction. Why? So that you can add the delta H's and find delta H for that reaction. All right, so that's what you're trying to do. So, for example, you want to get, notice that this has NO2 as a reactant. This first reaction has NO2 as a product, right? And NO2 is not found anywhere else in here, right? So you know you're going to have to flip this reaction and also multiply it by 1.5 in order to get a 3 there like you do in the sum. So just watch me do this. It's a little bit confusing at first, but it'll make sense in a minute. So what I'm going to do is I'm going to take this first reaction, I'm going to write it backwards, and I'm going to multiply by 1.5, okay? So that's going to be 3 NO2 goes to 3 NO plus 1.5 O2. And again, what I've done is I've taken this reaction, I've written it backwards, and I've multiplied it by 1.2. So what do I have to do to delta H?
Switch the sign.
Switch the sign and multiply by?
1.5.
1.5, exactly right. So that's 1.5 times positive 173 kilojoules. All right? That comes out to be 259.5 kilojoules. All right. The second equation, notice that it has things in the right place. Like if I look here, I have HNO3, that's a product there. The only problem is that this is times 4 and this is times 2, right? So what I'm gonna do to this one is just divide it by 2, right? So if I divide that whole thing by 2, I get N2 plus 5 halves O2 plus H2O goes to 2HNO3. All right. And now, since I divided it by 2, what do I have to do to delta H here?
Divide by 2.
Divide by 2 as well, or multiply by 1/2, which is the same thing, right? And that turns out to be equal to negative 128 kilojoules. Okay, then the last one I look at and I see, okay, what is a good clue here? Well, I don't have any N2 or O2 in this reaction, right? So somehow the N2 and the O2 have to cancel. And if I look up here, I have N2 and O2 here and here, right? And I have O2 over here, but I can base it on the N2. The N2 has got to cancel, but the only place N2 can cancel is here, right? So I'm gonna flip this last one. And now sometimes, you know, this will take a little more messing around than getting to it so directly like I have, but you'll see right here what I mean, NO. And so delta H for that, and I'm kind of, let me just, delta H for that one is just going to be equal to what? If this is plus 181, what is this going to be? Minus 181 kilojoules. Okay, so here are the 3 delta H's for the 3 reactions, right? Now, notice what happens, okay? I have, if I sum all these together, anything that's on both the reactant and the product side, I can cancel out, right? So I have, so NO2 is here. I don't have any other NO2, so I get 3 NO2, right? Plus, let's see all the reactants, N2. I have N2 and N2, right? And then I have, let's see, oops, did I forget to flip that one?
Would it be a positive 181? Sorry.
Sorry. I messed this up. Hold on. Sorry, I messed that last one up. That doesn't work out. This one should not have been flipped. It should just be written. It should just be. Why did that come out like that? Let me see.
I don't think you flipped it when you wrote it down.
Yeah.
You need to flip it.
Oh yeah, I think that's what happened.
Yeah. It doesn't flip.
I was a little confused by that too.
Yes. Sorry.
Yeah.
I didn't flip it. I just wrote it down straight. So it should be 2 NO, right? Goes to N2 plus O2. Okay, does that work? Let's see that. And that should be minus 81. Okay, that was my problem. I just forgot to flip it. All right, good. All right, so 3NO2, and then look what happens. The N2 and the N2 cancel, right? 5 halves O2 on the left, and then I have O2 plus 1.5 O2, right? So that's the same thing, right? That's also 5 halves O2, so that's going to cancel with the sum of this and that, right? So there's no nothing else there. And then I come down and I have H2O here, okay? And then I have, what else? Then I have NO, but the NOs are going to cancel. See, I have 3 here and 2 here. So that's going to cancel, and that's going to leave 1 up there. All right. And so what else do I have? That goes to, I got my H2O. Okay, so that goes to 2HNO3 plus NO, my other NO up here, right? So what's left after I canceled everything out? My 3 NO2s, right, on the reactant side, my H2O on the reactant side. Everything else on the reactant side canceled, right? On the product side, right, I have NO and HNO3 and everything else canceled. So in other words, these three reactions sum to this overall reaction, right? So therefore, delta H for this overall reaction is equal to the sum of these three delta H's, right? So that's 259.5 plus negative 128 kilojoules plus negative 181 kilojoules. And if I sum that all up, I get minus 49 kilojoules. So delta H for that reaction is minus 49 kilojoules. Okay, I know that was super confusing. I'm so sorry. It didn't help that I made this big mistake here in the middle. But the idea is that I'm giving these three reactions, and I'm basically going to play around with them until I can get them to sum up to the overall reaction that I want, right? I'm just going to play around with them until I can get to the overall reaction that I want. And as I play around with them, I got to remember to change the delta H's over here. All right, so for example, if I reverse this, then I got to change the sign of that. If I multiply this by 2, I got to multiply that by 2 and so on, right? But then if I can get them to add up to exactly this reaction, then the delta H's for this reaction will be equal to the sum of the delta H's for the individual steps. All right, and again, I have one for you to try, but we're all out of time. We're pretty much all out of time, so I'm gonna do the same thing as before. I'm just gonna pause here for a minute so you can go back and do this on the recording. Just gonna pause, blah, 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 okay? So you should pause the recording here, work out this problem, and I'm about to reveal the answer. The answer is C, okay? The answer is C. All right. All right, sorry that was really rushed. I hope you can get it from the recording, but I'll stick around afterwards too to clear any of this up too. So feel free to stick around and I can try to clear some of this up. Also, let's see, you have everything you need to be able to finish the problem set for this week. That's why I was trying to rush there towards the end. You should be able to finish it up. And next time we'll just do this last topic and continue from there. Okay. That was a tough one. Sorry, guys. All right. I'm going to officially end this dumpster fire and we'll chat. Thank you very much. Bye.
Thank you, Professor Trout.
Thank you.